Perfect.
So hello and welcome to lecture number 4, I think, September 9th. We have a question on the homework, so I'm going to load up, and you should as well, the chapter 1 homework at the end of the first PDF. And you said it was question number 8?
I think so, yes. Construct a probability distribution table for the sum of 2 tetrahedral dice. I just don't know what a probability distribution table looks like.
A probability distribution table lists every possible outcome in one column and the probability of getting that outcome in the next column.
Okay, got it. So like the sums.
Yeah, so it's like regular dice, but regular dice are 6-sided, right? Yes. So
Yeah,
regular dice, if I roll 2 dice, 2 regular dice, what are the possible values that I can get?
2 through 12.
2 through 12. If I roll 2 dice,
2 through 8.
2 through 8. And then what we want to calculate to complete the table would be how likely it is to get every one of those outcomes. So would questions 8 be similar to question 6's graph? Well, question 6 is referring to question 5, where you flip a coin 4 times. And maybe I'm misunderstanding the question. Harmony, what do you mean? Would question 8 be similar to question 6's graph?
Oh, I think I was saying that I think that if you did the probability distribution table for number 6, then it's the same thing as what they want for number 8, right?
Well, in theory, I mean, of course, the sample space is different.
Because the sample space is different.
Right, but the idea is the same. You're still calculating how likely every possible outcome is. That is what a probability distribution table is. The left column is your sample space. It's all the possible outcomes. The right column, well, maybe not sample space. It depends on what your experiment is. If I'm rolling 2 dice, for example, my sample space will be 1, 1, 1, 2, 1, 3, 1, 4, and so on. But if I'm interested in the total of the 2 dice, my column will be 2 through 12. Not exactly the sample space. It's more just a numerical value that I'm contemplating for whatever reason. Does that make sense? Yes, no, maybe so, a little bit, a lot, not at all?
Yeah, it makes sense. I got my confusion cleared up.
All right, Genesis, what's your question?
For question number 2 on the homework for 1.
For question number 2, okay.
I know the first 3 are zeros, but when I get to 4, I divide the 4 and the 20, and it says to round up.
Whoa, hold on a second. Okay. By the time the 4th flip has occurred, you've only flipped it 4 times.
Yeah.
Of those 4 flips, how many of them are R's? Of the first 4 flips, how many of them are R's?
1, right?
1. So you'd put 1 over 4, or 25%, or 0.25.
Oh, that's why I got confused.
20 hasn't happened yet, right? You're moving down the line 1 flip at a time, and you're adjusting your proportion based upon how many flips you've already done and their outcomes, not what you're going to be doing in the future. Right?
So then for the first 3, it would be like, for 1, it would be, what would it be? It was 1 out of 1?
0 out of 1.
0 out of 1. And then
0 out of 2, 0 out of 3, 1 out of 4, 2 out of 5, 2 out of 6, and so on. You're adding up the total number of successes, in this case R's, divided by the total number of flips up until that point. Does that make sense?
Yeah.
Yes.
Okay. Any other questions on anything that we've done so far?
I have one more question. I think I just got confused when doing the homework, but when it says the empirical estimate of the probability, are we just putting like 25%? Or if that would be basically, for this question, it would be like 25%.
Well, If they want the empirical probability after 4 flips, for example, the answer would be 25%, because your past data up until that point, 25% of the time you got R. If they want it after 5 flips, it will be 40%, because 40% of the time in the first 5 flips, you got R. So your empirical probability is based upon how many flips you've done and the outcomes up until that point.
Oh, okay. So then even at the last one at 20, which is 5/20 was 25%.
So the final answer would be 25%.
Okay, perfect.
Yes. So now that they are due, someone said, are you going to post them? So yeah, I'll post the solutions. Let me go ahead and do that now before I procrastinate too much and forget.
Similar to that, how would we go about solving B on number 1?
B on number 1.
Show how the proportion of side dot was computed.
Hold on a second. Let me find question number 1 here. How many of the first 6 tosses were side dots? So what's the answer to that? How many of the first 6 tosses were side dots?
2 out of 6.
8.
Well, there can't be 8 out of the first 6.
Oh.
Right? Out of the first 6, it was only 2 of them, right?
There was 2.
Right? So the empirical probability up until that point would be 2 out of 6. Yes? No? Maybe so?
Yes. Yes.
Okay. So I gotta find the solutions here in these files somewhere. I don't want to do it right now because we're in class and it'll take me a few minutes to find them. But I will post them today. And if it slips my mind, just send me an email and I'll get them up there today. And the quiz I'll get up there today as well.
Perfect.
Okay.
Thank you.
You're welcome. All right. So let's move on. We were on chapter 2's PDF. And we didn't finish it yet. I'm going to share my screen here. Okay, and let's take a look. Where were we up to? We did that. We certainly did that. We did random digits. We did random digits with different scenarios.
I think we're on page 20.
This graph on page 20 certainly looks familiar. I'm pretty sure we did this one.
Yeah, we're after that page. We're looking at it. Yeah, right there.
Okay, so let's remind ourselves of what this problem was. There were the iPhone activity was 5 people, and where was it? I guess it's pretty far up there, but the iPhone activity was 5 people put their iPhones on the table, and then they picked them at random, and we're curious, how many got their own phones. And of course, we don't actually need iPhones. We can do it with index cards. Just put A, B, C, D, and E in index cards and shuffle them and then pick them in order. And if the first one is A or the second one is B and so on, that's a yes, we got my own phone. So according to this table, according to this graph, where we are interested in whether or not one person, if exactly one person got their own phone, we see that the empirical probability seems to be roughly 35%. It seems to stabilize around 35%. Maybe it should be 33%. I don't know. I'd have to do the math. Here is a close-up of the last 100 runs. So first, what was the result on the last run? Was it a yes or was it a no based upon this graph?
No.
It was a no because we dropped, right? We dropped, which means the probability of a yes went down, and the only way that can happen is if we get an extra no. By how much did the run change the estimate from what it was after 499? Well, at 499, it was roughly 0.357. And after the next one, it dropped to 0.356. So it changed by what, 1,000th? 0.001, correct? Yes, no, maybe so?
Yes.
You guys with me? It's a pretty small change, which means we are far enough along in terms of run numbers where a yes or a no doesn't really change the probability that much. What was the smallest estimate of the probability during the last 100 runs? In other words, if I could have stopped any time amongst the last 100, in hindsight, where would I have stopped that would have given me the lowest empirical probability?
0.348.
0.348, right here. All right, this is the lowest, which is still pretty close to 35%. I mean, this entire run of these last hundreds doesn't vary by more than 0.348 to 0.364. We're talking about less than 100th of a percent, or approximately 100th of a percent. So we've really come to stabilization. If over the course of 100 runs, it doesn't change by more than 1% or so, you know that you've pretty much stabilized. And what was the largest? Even though I just gave it to you?
0.365-ish.
0.3645, maybe, something like that. You know, approximately that. You all agree? Does that make sense?
Yes.
Now, if I had gone all the way to 500, what would my estimate be of the probability that exactly one person got their own phone? And that would be, we got a chat.
0.356.
Okay, Katerina. Yeah, 0.356 would have been my final estimate. Okay, now, the theoretical probability is 0.375. So they're telling us right now that people out there who are pretty smart did some advanced math and came out that in theory, the answer should be 0.375. What is the size of the error if we stop after 500 runs? So after 500 runs, we got 0.356. The true value is 0.375. So what's the error between what we got and what we should have gotten?
You would subtract, right?
That's what I would do. When you say 115, 115.115 seems a lot better, but I think it's more than that. 356 to 0.375 should be 0.0.
0.019.
0.019. Yeah, that's what it should be. 0.019, which is less than 2%. Which is fairly close. Now, does 500 runs seem like enough for a reasonable estimate? It should be. Yeah, I mean, we're only a couple percent points off. I mean, if you look, we do have pretty good stabilization at 500, right? It should be a little higher. But remember that this is a contrived example. This didn't actually happen in real life. Nobody actually did this data. They just kind of made up a pretend graph. But even if it was real, is it so far-fetched a notion to think that after 500 runs, we'd be about 2% off? You can actually do the math on that, by the way, to calculate how likely it is after 500 runs to be 2% off. But certainly, had we gone to 1,000 runs, what do we think would happen if we had gone to 1,000 runs? If we had not stopped at 500 like here, but kept going all the way to 1,000, so had another graph the same size tacked on to this one.
It would stay stable like that?
Well, it would certainly stay stable, but I think it would kind of approach 0.375, because remember what the law of large numbers says. The more data points you have, the greater your sample size, the closer you get to the true probability. So if we're 2% off or 1.9% off and we did 500 more runs, I would expect to be closer to 0.375 than I am now. I don't know if I'd get there. Maybe I get there and overshoot the mark. Who knows? But that's what I would expect. And this is, again, the law of large numbers. The more runs you do, the closer your estimated probability is likely to be to the theoretical probability. Does that make sense? Yes,
Yeah.
can you so? Okay, now, there is a nice rule of thumb, which I want to cover for a second. But it's kind of obvious if we go back to that original graph, if we had done 10 simulations, you can see major fluctuation, right? Even 100, if I had stopped at 100, if I had done this to the right side and not, I don't know if you can see, I don't know, if I had done to 100 like that, even that, I wouldn't claim I'm stabilized yet. Correct?
Correct.
Correct.
So the question is, as a general rule, how far do you got to go before you can claim stabilization, before you can say, I'm confident that I'm in the ballpark? So the answer is that there's a nice little rule of thumb. And the rule of thumb says as follows. Suppose that you want to be within an error E. So let's say you want to be within 1% of the true value. 1% of the decimal is what again? What is 1% of the decimal? Anyone? Bueller? How much?
0.01.
0.01. So the rule of thumb says you do 1 divided by whatever error you want squared. In our case, if I want to be within 1%, I do 1 divided by 0.01 squared. And what do I get? What is 1 divided by 0.01 squared? What number is that? Take out your calculator. What is 1 divided by 0.01 squared?
Isn't it 0.0? Oh, no, divided by 9.
I got 10,000, am I right?
Yeah, 10,000. So the rule of thumb says that if you really want to be pretty certain that your empirical probability is within 0.01 of the true probability, you should do 10,000 runs. Now, we only did 500 in that graph. So it's to be expected that we're not necessarily within 0.01. But 500 still seem to be pretty stable. So I know that I'm fairly close, but not close enough. You can imagine in a real life situation, if money's on the line, if if you run a company and you're making some gadget and the gadget has a very small window of acceptability, that if it's too big or too small, it won't fit and it won't work right, that you really want to make sure that your gadgets that you're creating are the right size, you might really feel that 10,000 runs is necessary to make sure that it's close enough. Or maybe even 100,000 runs or 1,000,000 runs, whatever the case may be. Depending on how important it is to you, the smaller the error, the smaller the range of possibilities that you're willing to accept, the larger, the more numbers of runs you're going to have to do to guarantee that you're close enough. Does that seem reasonable as a conceptual idea?
Yeah.
Now, where did this formula come from? Well, people a lot smarter than you and I came up with it, but we just get it, we go with it, we move on. So if you want to be within 0.1, not 0.01 like we talked about, but if you want to be within 0.1, how many runs should you do to be highly confident that your value is within 0.1 of the true value? And someone chatted and said, no, not 10,000. 10,000 is for 0.01. We did that math earlier.
100.
This is only 100. If you only want to be within 0.1, if you do 1 over 0.1 squared, you get 100. If you want to be within 0.01, you need 10,000. If you want to be within 0.001, you need 1,000,000. So the smaller the error that you're willing to accept, the more runs you got to do to be within there. How about 0.05? How many runs would it take to be guaranteed, not guaranteed, but to be pretty certain that we are within 0.05 of the true value?
4.
How many?
I got 4.
Just straight up 4 runs?
Oh, no, I'm sorry. I know I got it wrong. I'm sorry. I didn't put the 0. Sorry.
400?
400. Okay, 4 runs. That seems pretty easy.
You're like, why did you even do it, huh?
No, exactly. Okay, 400. And we already know that 0.01 is 10,000. Now, national polls, like for example, who's going to win the coming election, or this or that, national polls usually have an error of 3%. They want to be certain that whatever value they have is within 3%. How many runs must they do to be fairly certain that they are within 3% of the true value? This is for everyone, so don't think it's just for the person next to you. Feel free to answer. How many runs do we need to do to be fairly confident that we are within 3% of the true value? What's taking so long? What's wrong?
Is it 1,000?
Not exactly 1,000. Where do you get 1,000 from?
I guess.
Ah, you guessed, but we have a formula. Why guess when we have a formula?
I missed the formula.
You missed the formula. The formula was right here.
Yeah, that would Lisbeth got.
Oh, okay, let me write it down.
The
Sorry.
number of runs is 1 over error squared. Now, Lisbeth said 1111.1111. Because what Lisbeth did is she did 1 divided by 0.03 squared and got this number, 1111.1111. However, a run, you can't have a decimal number of runs, right? You can't poll 1/10 of a person. I don't care how insignificant the person is in your life, we still don't consider them 1/10 of a person. So we have to round to a whole number, which is why in the question, it doesn't say exactly, but it says about what sample size do you think they use? About what sample size do you think they use to be within 3% of the true value? If you follow the formula, you get 1111.1111, which is a decimal. So we have to round that. What's a good number to round that to? The number was
1,111.
So the number that we got mathematically was this. And I said, where do you round it to? And you said, I want to round to 1111. But I actually want to round it to 1112. And the answer is not because of your usual rules of rounding. Obviously, the usual rules of rounding don't go up when you have a 1 in your decimal. The reason why it would go up, though, is because this is the minimum number that math gives me according to that formula. Any number smaller than this doesn't quite cut. So I want to go to the smallest number that I can find that is not smaller than that. So I'm not rounding per se, but what I'm doing is making sure that I'm not underneath my cutoff. And the way to do that is actually to go up to 1112. Does that make sense? Yes, no, maybe so?
Yes.
Anyone? I hope so. I hope so. And that is the end of homework 2. So we are now done with the second section. Your homework, again, not to be handed in, but just to be done for the sake of understanding. Do it, essentially do it on your own. And next weekend, we will have a quiz on chapter 2. What do you think about that? Well, I think it's great. So, and of course, that's all that matters. Okay, so are we all ready to begin chapter 3?
Yeah.
Yeah.
All right, I was thinking of more of like a Braveheart, like everyone cheering and screaming, and I got like 2 people, which
We're getting there.
you're getting there. Okay, all right. You know, Mel Gibson, I am not for good or for bad. Okay, so chapter 3, rules of counting. Now, some of you might be thinking to yourself, I know how to count. I've been counting for a very long time. You know, you do the 1, and then next comes 2, and then next comes 3, and so on, right? We're pretty good at counting. But that is not what the mathematics of counting is all about. In fact, one of the most challenging branches of mathematics is called combinatorics, and it is the mathematics of counting. So what do we mean by the mathematics of counting? What I mean by that is as follows. If I ask a question like, 10 people walk into a room, there are 20 seats. The 10 people all pick a seat to sit down at. How many different ways can they be seated after they all decide where they want to sit? That would be a question that would fall into the purview of the mathematics of counting, because we don't want to say, okay, well, they can all be there, that's 1, or they can be here, that's 2, or they can be like this, that's 3, or they can be like this, that's 4, because we're talking in the millions, or the billions, or the trillions of different possible ways things could be arranged. So rather than brute forcing it, we want to come up with formulas and ideas that can help us calculate how many of something occurs. And that's what the rules of counting is all about. And we start with the fundamental principle of counting. And that's as follows. And here's a simple example. You're getting dressed in the morning. And let's assume, like me, you have no understanding of fashion. So you don't worry about what goes with what. It's just a matter of getting dressed. And you have 5 shirts that you can wear. So let's say there's 5 shirts. And there's 7 pants that you can wear. So 5 shirts and 7 pants. And you have to pick a shirt, just 1, and you have to pick a pair of pants, that's 1. Why is it called a pair of pants when it's only 1? That's a whole nother question. I'm sorry. Okay, whatever.
And same for sure. I actually asked the same thing last week.
Yeah, so it's not, you don't wear a pair of shirts, you just wear 1 shirt, but you wear a pair of pants. Like a pair of shoes, I get, because there's 2 of them. It's a pair of shoes. I get it. But why is it I don't know.
Pant is just 1. There's
Huh?
a pant leg is 1, and then the 2 of them together.
Okay, so a sleeve is 1 also. How come it's not a pair of shirts?
Well, yeah, but oh yeah, I guess you're right.
See, you have a pair of legs, it's true, but you got a pair of arms.
We could be calling shirts a pair of sleeves.
That's true. Anyway, these are questions that plague me at night. That's why I have trouble sleeping. But anyways, let's move forward. Suppose you have 5 shirts and 7 pants. How many different outfits are there?
35.
So there's 35. So some people say 12, which is horrible. It's not 12. You don't add shirts and pants, but you do multiply, because what's happening is essentially you're making 2 choices. You first choose which shirt you want to wear, and you have 5 choices. And then for each one of those 5 choices, you have 7 options for which pair of pants, yeah, I said it again, for which pants you want to wear. So this is the fundamental principle of counting. It's based upon multiplication. And it goes as follows, right? Example, oh my God, look at that. Wow, crazy. So Pat has 4 shirts and 3 pair of pants. See, they can't even spell right. 3 pair of pants. Even I know better than that. How many different ways can Pat pick a shirt and a pair of pants to wear? So what's the answer? 12. And you can see it in this area model. What is it called, an area model? Because it's like length times width. It's like a rectangle. And you see that you have 4 shirts, a red shirt, a blue shirt, a green shirt, and a black shirt, for example. You have 3 pants, blue, black, and white. Every square represents a combination of a shirt and a pant. Shirt and a pant. 1 shirt and 1 pant. I'm going to go with that. So red shirt and blue pants right here, red and black here, and so on. You can see there are 12, correct? Now, If Pat picks clothes at random, what is the probability that Pat's pants and shirt are the same color?
212. Is it 212?
16%.
I'm sorry, I heard someone answer, but it was like talking in the background. What was your answer?
212.
2/12. Do we agree with this?
Yes. Blue and black and black.
Right. So there's two ways of the 12 equally likely outcomes that the pants and shirt are the same color. Now, those of you who are familiar with fashion, is that allowed? Pants and shirt are the same color?
No.
You can't do that, right?
No.
It all depends on how cool the person wearing it is. I think.
That's true. If you're cool enough, you set fashion trends yourself, right?
Maybe different shades of the same color.
That's true as well. All right. So it's all about coolness, and coolness.
Coolness.
We're gonna pretend we're not gonna talk about this anymore. We're gonna move forward. So that is an area model. There's also what's called a tree diagram, which, to be honest, is my preferable way of thinking about it. With a tree diagram, you think of your options sequentially. So you think of them, unlike the area where I don't really care which is first and which is second. I just list the possibilities. For a tree, I think of it sequentially. I'm first picking my shirt, and there's 4 options for the shirt. And then I pick the pair of pants, and there's 3 options if this shirt was chosen, and 3 options if this shirt was chosen, and 3 if this one was chosen, and 3 and this was chosen. Either way, I see there's just 12 outcomes, right? Somebody tell me, what is the advantage of the area model, and what is an advantage of the tree diagram?
Well, for this one, I could see it more clearly now. Like you have them listed down the middle.
For which one? You like the tree diagram more or the area diagram more?
Well, for the tree diagram, it's just easier to see. You just have them all listed down, like the colors. And it's all just, you know what I mean? I don't know if I'm explaining yeah.
I know, I totally understand what you mean. But what would be an advantage besides ease of viewing, which is 100% a great advantage. I mean,
yeah,
we love. I love looking at data and having an easier time reading it just because of visualization. But besides that, give me another advantage of the tree diagram, and I'd like an advantage of the area diagram. I want to give a reason why each one has their place. Besides visualization, which 100% is valid, but there's another reason why this is better, and there's a reason why this is better. So can anyone think of a reason why one will be better than the other?
I feel like with the area model, it was easier to answer the question of whether or not Pat's pants and shirts were the same, because it's easier to kind of map out than it would be with the tree diagram.
Okay. So again, that's a visualization answer, correct? Easier to see, right?
Yes.
Okay, so I'm looking for something beyond just visualization, which is 100% valid, but I'm looking for something beyond that. Give me something beyond visualization as to why this model is better than this and why this model is better than the other.
For me, the area model is quicker to make.
Okay, so the area model is quicker to make. Okay, I don't have to repeat red, blue, black, white over and over and over again for each different shirt. So if I had 10 shirts and 10 pants, it would be a lot quicker to make the area model than the tree diagram. Do you agree with that?
Right, yes.
Okay, that's a great advantage for the area. Now, what's an advantage for this one?
I think the tree diagram is helpful when like order matters, when like you have to do something in order.
100%, 100%. And there will certainly be times later where we have to do things in order. This one, in theory, I could have done either way, correct? For shirts and pants. In theory, I could have done either way. But you're 100% correct. When order matters, you certainly want to do the tree diagram. But what I'm looking for is a little bit deeper. What if I have 3 choices, shirts, pants, and shoes? Could a tree diagram handle that scenario?
Yes.
Could the area diagram handle that scenario?
No.
No, not unless I want to go into the third dimension. So area diagrams can only handle 2 choices, whereas tree diagrams can, in theory, handle as many as I want. Does that make sense?
Yes.
So your answers were 100% correct. I'm not discounting them. It wasn't what I was looking for, but 100% valid. If the order matters, certainly a tree diagram, and also in terms of visualization, it's a lot easier to see here for some. 100% true. Mine was just something else that I was looking for. Usually, quite often when I ask a question and I'm thinking of a specific answer, I tend to discount things that I'm not thinking of, but that doesn't mean they're wrong. It just wasn't what I was going for. So here's another example. The Honda Civic LX comes in 2 interior colors and 8 exterior colors. Without actually doing anything, how many options do we have here?
16.
16, 2 times 8, correct?
Yes.
Now, without actually constructing it, would we be able to make an area diagram here?
Yes.
Yes, it shouldn't be a problem, correct? We also, is there any question on how we would do that?
No.
I don't want to just assume that you all get it just because I think, it's straightforward. I want to make sure that you guys think it's straightforward.
Interior color and exterior color, right?
Yeah, so interior on one axis, right? Exterior on the other axis. And it's very hard for me to write with this thing, but you list all your exterior colors and your interior colors, right? And this will give you your, this will give you your diagram, right? Your area model, correct?
Correct.
Okay. What about a tree diagram? Could we make a tree diagram with the same scenario?
Yes.
Okay. Which would you prefer as your first choice, exterior or interior?
Interior.
And why?
It's only 2 choices.
For interior, there's 2, and exterior, there's 8, right?
Yeah.
So which would you prefer to be your first? In your tree model, you always make a choice as your first, right? So here's starting points, and then you make your first, and then from them you make your second. Of course, this is always tuning. Huh?
Exterior first.
Why?
Because there's more options.
Yeah. If I did actually, I don't know about that. I don't know if it makes a difference. If I do 2, 2, then there's 8 guys coming out of each one of these, right? Right?
Yeah.
Yeah.
If I do 8 first, and then 2 out of each, I'm not sure if that necessarily saves me time or not. Right? I guess it depends on how neat I am and how
you can get in the rhythm. If you're just writing the 2 multiple times, you're writing black and gray, black and gray.
Yeah, that could be it, right? Black, gray, but BG, 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 or something like that. Again, there's one way is as good as the other in theory. But this here is now the official fundamental principle of counting. If there are A ways to do one thing and B ways to do a second, then there are A times B ways to do both. And if there are C ways to do a third, then you multiply all 3 of them to do all 3, and so on. This is the fundamental principle of counting. And we can use it for some old examples. If I flip 5 coins, how many different outcomes are there?
2.
2. So this is it right here. Someone just said 10. Someone just said 10, but they didn't use, I'm not going to call you out whoever you were, but you didn't use the principle of counting. The principle of counting says if you do a sequence of actions, 5 flips, that's 5 actions, correct? How many outcomes are there for the first action? Which is the first flip.
2.
How many outcomes? How many? 2. How many outcomes for the second one?
2.
How many for the third?
2.
For the fourth?
2.
For the fifth?
2.
So you don't just multiply 5 times 2. You multiply 2 times 2 times 2 times 2 times 2, which gives you what?
32.
32 different outcomes. Heads, heads, I can't even write it, but 5 heads in a row, and then 4 heads and then a tail, and then 3 heads, 2 tails, and go through all the different possibilities. But it's not 2 times 5. It's not 5 actions, 2 each, therefore 10. It's 5 actions, 2 each, therefore 2 to the 5th power. Does that make sense?
Yes.
And what is the probability of getting all heads in 5 flips?
1 out of 32.
Well, only one way to get all 5 heads, and there's 32 total equally likely outcomes. So the answer is 1 out of 32. Now, could an area model be used for this case?
I think, yeah.
Remember, an area model, each action has a dimension. So the first action will be this way. The second action will be this way. What dimension are you going to use for the 3rd, 4th, and 5th actions?
Never mind, no.
Never mind. Okay, area models can only be done when you have 2 actions. Could a tree diagram be used?
Yeah.
Oh yeah, a tree diagram, you have your first one, 2 options, 2 from this one, 2 from this one, third, 2 from each, 2 from each, 2 from each, and so on, and so on for the 4th and the 5th. Does that make sense? Yes, no, maybe so?
Yes.
A little bit? Okay. So that takes care of the fundamental principle of counting, which is our very first major counting principle. The next one are permutations. Anyone familiar with this child's toy?
Yes.
Good, me too. I used it just yesterday. It's a lot of fun. Now, is anyone here familiar with the Towers of Hanoi problem?
Yeah.
Anyone know the Towers of Hanoi?
No.
You have 3 rings.
Yes.
And then you have discs. And you want to transfer the discs to another one, but you can't have a smaller one underneath the bigger one.
Oh, yeah.
And
Monkeys do that, I think.
Yeah, it's a lot of fun. I remember doing it as a kid, just like yesterday. It was a lot of fun. Okay, anyways. So this toy for children has 6 rings of 6 different colors and different widths on a single post. So this is not the Towers of Hanoi. This is just one post with 6 rings. Now, imagine all 6 rings are off and are sitting in front of you. How many different ways could you put the first ring on the post? How many options do you have for putting your first ring on the post?
Six?
6. It could be any one of the 6 rings, correct?
Yes.
Right? Any one of the 6 could be the first one on the post. I'm going to actually erase that for a second, scroll up so I can write more. Okay. So the first one, it could be any one of the 6. Now, once you've put the first one on, how many choices do you have now for the second?
5.
Once you put them on, how many for the third?
4.
4.
And how many for the fourth?
3.
And how many for the fifth?
2.
And how many for the last?
1.
Lift off. Oh, yes. Okay. So how many ways are there to put on all 6 rings?
Would you have to multiply everything together?
Isn't that the fundamental principle of counting?
Yes.
That when you have a sequence of operations of this many options for the first and this many options for the second and this many options for the third and so on, you just multiply through, correct? Right? So by the fundamental principle of counting, we're going to call it the FPC because it takes me forever to write with this. By the fundamental principle of counting, how many ways are there to put on all 6 rings?
I got 720.
720 ways. Now, the largest ring is supposed to be in the bottom, and the second largest ring, and then the next, and so on. If the kid put them on at random, what is the probability that they're going to be in the right order? How did you get 720? 6 times 5 times 4 times 3 times 2 times 1. 6 options for the first, 5 options for the second. 6 times 5 is 30, times 4 is 120, times 3 is 360, times 2 is 720, times 1 is still 720. Does that make sense? All right, fundamental principle of counting, 6 times 5 times 4 times 3 times 2 times 1. So what is the probability that the kid put them on in the right order?
1 out of 720.
1 out of 720, which means if you turn your back for a second and the kid says, I did it, and you turn and you see them in the correct order, will you assume the kid knew what they were doing or they got really, really lucky?
They got lucky.
Really? 1 in 720? Really? 1 in 720? You're going to assume they got lucky? That's like never going to happen, 1 in 720. Sorry, you have high standards for your kids. That's all I can say.
Maybe I was like, he's a genius. He's a little baby genius.
Yeah, well, if it's a baby genius, it's not luck. If it's a baby genius, he knows what he's doing. Now, by the way, does anyone know a shorthand for 6 times 5 times 4 times 3 times 2 times 1? Anyone learn in their mathematical career?
Involves an exclamation point. Right?
Yes, yes. So a shorthand notation for multiplying down to 1 would be 6 with an exclamation point. Now we don't read it as 6. That's not what the exclamation point is telling us. This is read as 6 factorial. F-A-C-T-O-R-I-A-L. Factorial. 6 factorial means 6 times 5 times 4 times 3 times 2 times 1. Okay, you all with me so far? And this notation we're going to use throughout the course. This factorial notation. So make sure you're familiar with it. 6 factorial. All good so far?
Yes.
Yes.
Okay, so how many ways are there to put on just the first 2 rings and not worrying about any of the rest? I can't hear you. What?
No, I'm sorry. I'm reading the question.
I understand. How many
Would
ways?
it be 30?
Yes, 30, because the first action again was 6, the second action was 5, and by the fundamental principle of counting, 6 times 5 is 30. How many ways are there to put on just the first 3?
120.
120, 6 times 5 times 4. Agreed? Yes?
Yeah.
No? Maybe so?
Agreed.
Yes.
Okay. So now we have our second principle of counting. First, there are n factorial ways to line up n objects. And the last example illustrated that. If you want to put 6 objects in a row, 6 choices for the first, 5 choices for the second, 4 for the third, 3 for the next, 2 for the next, 1 for the next, 6 times 5 times 4 times 3 times 2 times 1, 6 factorial. If it was 10 choices, 10 objects, 10 for the first, then 9, then 8, then 7, 6, 5, 4, 3, 2, 1, 10 factorial. So there's n factorial ways to line up n objects. But suppose you don't want to line up all n of them. Suppose you only want to line up r of them. So there's how many ways for the first one? If you're going to line up r objects, how many ways can you line up the first one of those n objects? Right? There's n objects in front of you, n objects, and you are going to pick R of them. So you're going to line up R of them. How many choices do you have for the first? Anyone? Hello? You have n objects in front of you. You want to pick R of them. Think of actual numbers. Suppose there's 10 objects in front of you. You're going to pick 4 of them. How many choices do you have for the first one that you're going to pick?
10.
10. How about for the next one?
9.
9. How about for the next one?
8.
How about the next one?
7.
How about the next one?
6.
Trick question. You don't have 6. You're only picking 4 of them.
Oh,
You failed, right? 10, 9, 8, 7. In terms of N and R, there's N ways of picking the first one, N minus 1 ways of picking the second one, N minus 2 ways of picking the third one, and N minus 3 ways of picking the last one, correct? Agreed?
Yeah.
Now, this 3 is 10. Actually, you know what? Let me do one thing here, make it a little more clear. The first one, I'm not going to write as 10. I'm going to write it as n minus 0. So n minus 0 ways for the first, n minus 1 way for the second, n minus 2 ways for the third, n minus 3 ways for the last, correct? Yes?
Yeah.
With me, am I going too fast and not understanding? Speak up now or forever hold your pieces. So the last one is n minus 4. Where's my eraser? Sorry. Is n minus 4 plus 1. Do you agree? 3 is the same thing as minus 3 is the same thing as minus 4 plus 1, right?
Yeah.
Why did I write it like that? Because 4 is R. So I go to negative n minus R plus 1, which is this guy right here. N minus R plus 1. You go n down to n minus R plus 1. But this formula right there is a shorthand for the answer to the question. So I don't have to worry about all this stuff. I can go right to that formula right there. In our case, if I have 10 objects and I'm picking 4 of them, how many ways are there of lining them up? What does it say? Someone give me the answer. This formula right here, if n is 10 and r is 4, what is this?
N factorial divided by n minus 4.
What is n?
10.
How much?
10.
N is 10. And 10 minus 4 is?
6.
So it's 10 factorial divided by 6 factorial. Now, someone in chat said an answer which may or may not be correct. I'll check right now. But what I'm going to do, if you have a nice calculator, I'm going to show you what I'm doing here just so you can see it. I'm going to pin myself. So if you have this nice calculator here, I hit the math button to do math. And I'm going to move to the right to probability. And you see the fourth one on the list is the exclamation point. So I'm going to do 10 and then hit that button, factorial. 10 factorial divided by 6 and hit that button again, factorial. So I put in 10 factorial divided by 6 factorial. I hit enter and I get 5,040.
Wait, Professor, why is 6 factorial?
Wasn't it n minus r, 10 minus 4?
You didn't have to do the +1.
No. That was just deriving the formula. But this is just the formula right here.
Okay.
N factorial over n minus r factorial. If n is 10 and r is 4, if there's 10 objects, but you're taking only 4 of them to line up, it's 10 factorial, which the calculator can give you, or you can do 10 times 9 times 8 times 7 times 6 and so on, over 6 factorial. Which my calculator.
Do you mind doing one more example?
I'll do a few examples.
Perfect. Thank you.
Okay, let's see what comes next. How many ways can 5 teachers be assigned to 5 classrooms? Right.
Sorry, Professor. I'm
Yeah.
sorry. Before you move on, can you let me see the answer again? What did you get?
5,040.
5,040.
Thank you.
So how many ways can 5 teachers be assigned to 5 classrooms?
5 factorial.
5 factorial. Because you're going to use all 5 of them. The first person, the first teacher has 5 choices for which classroom they're going to go to. The next one has 4. The next one has 3. The next one has 2. The next one has 1. So what is 5 factorial equal to? 5 times 4 times 3 times 2 times 1.
120.
120. So there's 120 ways that 5 teachers can pick 5 classrooms. Now, 5 teachers are to be assigned to classrooms, but only 3 of them are available. So 2 teachers will have to wait. How many ways can the assignment to available classrooms be done? So in this case, choose your N wisely, choose your R wisely, and then go to the formula. N is the number of objects that we are going to line up from, right? We're picking a subset of a collection. How many objects are we choosing? And how many are we choosing from? What's our N and what's our R going to be in this example?
Our N is 5.
5 teachers.
And then our R is 3.
Our R is 3. We're picking 3 of them. Correct?
Correct. So we just divide 5 factorial.
So n factorial divided by?
3 factorial.
Not 3. What's the formula, let's say?
5 minus 3.
And what is 5?
Oh, okay.
What is 5 minus 3?
2.
So 5 factorial divided by 2 factorial.
It came from the only 3 available. There's only 3 available teachers. They're asking in the chat, Professor.
1 second. I thought I saw the chat. Oh, I was scrolled up. So where did the 3 come from, right? So there's 3 classrooms are available, correct? Right?
Yeah.
So there's, oops, I don't want to go too far down. So we have 5 teachers who walk into school. And we say, sorry, we don't have enough classrooms to go around. 3 of you are going to get classrooms. 2 of you will have to wait. So we're only going to pick 3 of those 5 teachers to get classrooms. How many ways can we do that? Well, there's 5 teachers and we're picking 3 of them. So we're going to pick 1 for the first classroom. Then we're going to pick the next person for the second classroom and the third person for the third classroom. So the formula says the number of objects we're picking from, factorial, 5 factorial, divided by the difference between how many we're picking from and how many we actually pick. So we have 5 that we're from, 3 that we actually pick. 5 minus 3 is 2. What is 2 factorial equal to?
2.
2, and therefore the final answer is 60.
You got 60, perfect.
Sorry?
I just wanted to make sure you got 60. I wanted to confirm.
Yes, no, so 120 over 2 is 60. We all agree with that? Does that make sense?
Yeah.
Let's do more, because the more we do, the better. 5 teachers are to be assigned to 7 classrooms, so that 2 classrooms will be left over. How many ways can this be done? So we got to choose what our N is referring to and what our R is referring to.
Our N is 7.
Our N is 7. And our R is going to be?
5.
5. In this case, we're counting classrooms. 7 classrooms, and we're going to pick 5 of those classrooms. In the last example, it was 5 teachers, and we're going to pick 3 of those teachers. Here, 7 classrooms, 5 of those classrooms. So how many ways can we make this choice? What's the formula going to be?
7 factorial over 2 factorial.
7 factorial over 2 factorial, which is 25, 20. Could someone check my math?
Yeah.
I got that too.
All right, 25, 20. So there's 2,000. How are you computing it mentally? Well, I will walk you through my process. So earlier we did that 6 factorial was 120, correct? We did that earlier. Do you agree?
Yeah.
We have 5 factorial.
Sorry, yeah, sorry, 720. Earlier we did 6 factorial was 720. That was the very first thing we did with the kids' toy. We did 6 factorial equals 720, right? So then what I did is I divided that by 2. Where'd it go? I divided that by 2, and that got me 360. So now what I need to do is I need to do 360 times 7, right? Because we want 7 factorial. So 6 factorial is 1 times 2 times 3 times 4 times 5 times 6. But I need 360 times 7. So I did 300 times 7. That got me 2,100. And then I did 60 times 7. That got me 420. And then I added them, and that got me 2,520. That was my mental process. Nothing extraordinary. Just you know, experience, a lot of experience with arithmetic. So I naturally just know how to, or at least have an easier time computing things by breaking them up into smaller problems and then putting them back together at the end. Hopefully that makes sense. It did in my head, and then I just started to ramble. Okay, anyways, the next section is combinations, which is a 3rd principle, but I don't want to start because we don't have a lot of time yet. So we will end here after page 7. And we've done the fundamental principle of counting and permutations. So again, the first quiz will be up and the homeworks will be up today, tomorrow, the latest. You'll still have the entire weekend to do it. So by next Tuesday, make sure it's in the next time we have class. If I do not get it in today, which is certainly possible, I'm working today till 11 right now. So it's possible that it slips my mind. Please email me tomorrow morning or tonight and say, don't forget, in case I do. But I'll put up the solutions to the homework. I will put up the quiz. And we're roughly halfway through chapter 3. So you're also, besides chapter 2 homework, you're more than welcome to begin your chapter 3 homework as well. Yeah, so I'm going to stop recording now.